Today we start on a new chapter and start on something that might look kind of familiar, but mathematically it's significantly different from everything that we've been doing so far. And that is to consider functions of several variables. Before we begin, though, let's take a recap of functions that we've been dealing with. And we will include our function that we dealt with when we were in pre-calculus. So we usually write y equals f of x, and then that is a function that takes a real number and gives it as an output another real number. Sometimes we say x is your input, and then your output is f of x or y. So these are the functions that we know of from pre-calculus before we came to this class. This is background that you should already know. And then we can find domains and ranges and stuff like that. We can graph it. We can do stuff with it. This semester, we started to talk about these vector functions. That can either be sent to through 2 or 3 dimensions. And so I'll put 2 dimensions here for now. And then we have a notation for that to describe it as a function that takes an input, a scalar as an input, and then outputs something that is beyond the scalar. So a vector, a point in 2 dimensions or in 3 dimensions, depending on how we want the function to look like. And sometimes we say it takes an input, t for your input, and then your output is x of t, y of t. Okay? So all we did was take one chapter and we defined this vector valued function, and then we did all the calculus that we can do with it. And the calculus that we did with it included things like finding the tangent line, so derivatives, going from acceleration to velocity to position, so antiderivatives. And the tangent line involved tangent vectors, so we included the unit normal and stuff. Am I recording? Okay. All right. So that's what we did in the past. Today, when we talk about this new stuff, we're going to look at it in a couple of dimensions, a couple of different dimensions. We're going to consider, and usually the convention is to consider a function of 2 variables as something that can be set equal to z. And what we have here in this case is we take our f function, and then our input would be, well, you can look at it either as points or vectors, but regardless of how you look at it, it's something that comes from 2 dimensions or 3 dimensions. And then what's our output? Just r, yeah, scalar, z. So this thing is going to produce a scalar, and your output is just r. So instead of looking at it as taking a point, a scalar, and then off to something else, instead of your input being a scalar, your input will actually be a point, and then your output would be your z, or I guess we should call it f of xy. No, not an inverse. Not at all an inverse. It's a totally new type of function. In fact, sometimes we might extend this to another dimension where you look at it as a function of 3 variables, and in this case your function takes in x, a y, and a z, so something from R3, and then it outputs w, which is just a scalar. And then this is what you would come out with. Okay? So, are you guys ready for this? Yeah? The purpose of this is to take a look at another type of function. So we've taken a look at the simple functions in R, from R to R, and we took a look at vector functions and imagine how curves would look like. Now this is just another function that we can do calculus on. And really, when they say multivariate calculus, this is what they mean. This is really the heart of this class, is to take a look at and study these functions. All these other, the vector valued functions and the vector that we studied in chapter 13, are, they have their own right. They can be considered their functions themselves, and then they have their own special properties. But we're really, what we're going to do is we're going to use those as tools to really study these types of functions. Okay, so in chapter 10 we studied polar coordinates and we studied parametric equations. In chapter 13 we studied vectors and vector functions, and then we found a relationship between vector functions and parametric equations to say, oh, they're essentially the same thing. But all those really are tools for us to be able to study these types of functions. Okay? All right. To examine a type of function that we already know of, or we have seen before, we could take a look at either the saddle or the paraboloid as an example, because the saddle or the paraboloid can both be written where z is by itself. Right? So let's take a look at one of them. Let's take a look at the saddle. Where we're looking at z is equal to x squared minus y squared. And then imagine writing this as f of xy equals x squared minus y squared. So we can look at this as a function that takes an x and a y value and then gives us a z value, which is just a scalar. Okay? So back in pre-calculus or even algebra, when we learned about those really simple functions, f going from R to R, when we first learned about those functions, you know, we did a couple of simple things, like we tried to find numerical values of those things by making a table. And then what else? We tried to graph them. And then we tried to examine how those functions would be different from all the other functions that we're learning. So we can begin by making a table of values. So looking at this from a numerical point of view, how is this going to look like, or how can we describe this from a numerical point of view? Now, if we go at it kind of with nothing in mind, just say, okay, we're going to find some values. We used to make a table, so let's make a table like this. What is going to be the header for your left column? It's your input, right? So it should be XY. And then what's your output for your Y column? F of XY, or we can just say Z if we're going to let that equal a Z. And then we can plot points. Now, this might be a little tedious, but we can do it, right? 0, 0. And when I say points, we have to actually find ordered pairs and then figure out what happens when you put it into the function. So 0, 0, 0, 1, 0, negative 1, 1, 0, negative 1, 0, 1, 1, negative 1, 1, negative 1, negative 1, 1, negative 1. Tedious, right? But we can certainly find these values. So when x is 0 and y is 0, z is going to be 0. When x is 0, y is 1, this is going to be negative 1. When x is 0, y is negative 1, it's still going to be negative 1, etc. So let's see if we can fill this in properly. 0, 0, 0, 0. So that got kind of tedious really quickly. Is there another way to try to express this table? I just have like a regular table where you have two column table. Is there another way to try to view this table? What? 3 column? What? Graph? We're going to get to the graph in a minute, but I'm just talking about finding numerical values of these things. 2 tables? Well, with respect to a parameter, we could, okay, but I guess the table that I was thinking about kind of looks like this. Instead of I don't know how you would call this, maybe a one-dimensional table. Instead of like a one-dimensional table, maybe we can consider a 2-dimensional grid. Something like this, where you would have 0, negative 1, negative 2, 1, 2, and negative 2, negative 1, 0, 1, 2, 3. Where you would have, whoa, wait a minute. Let's cross that one out. Maybe these would be your x values, and then these would be your y values. So you have the x and the y, the 0, 0 business over here. So when x is 1, y is 0. I think that's going to be a 1. When x is 2, y is 0. Should be 4, right? 2 squared minus 0 should be 4. This would be positive 1, right? So if we do it this way, we might get things a little bit faster than what we were doing over here, right? We only have to write 0 in for x one time, and then we can find a bunch of values here for the rest of the table. Does this table make sense? How we're creating this table? All right, let's see if we can fill it in. Maybe I should have used different colors for that one. Let's use red or something different. So 0 for x, if x is equal to 0, 0 for y will give me 0, 1 for y will give me -1, 2 for y will give me -4, and then -9. So 0, -1, and for y would be +1 with a negative, so it's still -1, -4. And then when x is equal to 1, y is equal to 1, this is 0, I think. This is 0. So in our table, our long table over here, we've really just captured this much amount of data, but with a two-dimensional table like this, with not much more information, we can fill in the rest of this table without extending some long vertical table here. So let's figure out the rest of them. When x is equal to 2, y is equal to 1, this is 3. Is this going to be 3 also here? When x is equal to 2 and y is equal to -2, 0, 0. Okay, when x is equal to 1, y is equal to -2, what's that going to be? -3. When x is equal to 1, y is equal to 2, this is also -3. Etc. I guess we should figure out these other points. What's this one? -3 also. Okay. So looking at this numerically, we kind of see some patterns here. I should have added another row with -2 for the x values. But we'll leave it like this and get some idea of what's going on. So there's some interesting patterns to kind of examine here. It looks like we got a bunch of zeros going over here. We got negative values here, and we got positive values here. So that, whoa, look at this drawing. It kind of looks like a hyperbolas, huh? So with that idea in mind, we kind of get to the next step of trying to visualize this using a picture. And now visualizing this would be another interesting thing to do. Okay. So the point is that you can view these functions of several variables numerically, but instead of using a table like we used to use in the past where you have 2 columns, it might be good to use a two-dimensional table like this where we can have a 2x2 expression, and then all the numbers inside would be your z values. The numbers on the left side would be your x values. Number on top would be your y values. And by doing that, we might get a better sense of how to describe this numerically instead of, doing that table. So the next step is to try to visualize this. And so let's do that. Let's label this. This is we're looking at things numerically. So the next step is try to imagine how things look like graphically. So again, we'll stick with the saddle. Z is equal to x squared minus y squared. And let's imagine how this is going to look like graphically. Where do you begin? Well, again, we could do the plotting points business. flop. So I won't recreate this whole business, but plotting points, usually we would take some x value and a y value, put it in an x-y axis. Plotting points here would be a little bit stranger because of the fact that your input is something in R2 and then your output is something in R. You kind of have to imagine putting a couple of things together. One thing you need to put is the xy plane together with a z-axis. Well, I think there's only one way to make sense out of putting those things together, and that is exactly that three-dimensional x, y, z axis put together that we have. Okay? But now our input is not just a scalar number, but an input would be a two-dimensional region. So it turns out that all the possible inputs, which we usually call our domain, is going to be whatever dimension you're coming from. In this case, it's a two-dimensional region. And then at some value in your region, you're going to get mapped into some point in Z. So let's imagine how that's going to look like. That means if I take some point in my x, y plane, that should be able to map to some z value, right? So that's going to give some height, some z value. That's kind of hard to picture. That's a good thing we have Mathematica. So let's take a look at plotting some points. For our function. And so what I'm going to do is I'm going to plot points. Whoa, what's this? In a region from -4 to 4 in the x and -4 to 4 in the y. So this is if you look at it directly from the top, you just see points where x is equal to 0, 1, 2, 3, 4, y is equal to 0, 1, 2, 3, 4, negative also. And this is what you would see, right? Just basically a grid. But each of those points, when you put that into the function, will give you a height. And the height that we're saying is going to be your z value. The height is the scalar value that you get when you put those numbers into the function. And so to look at it from a different point of view, you kind of start to see what you should be seeing. Is it, can you see? See some dots? All right, well, the point is, if I just pick points -4, -3, -2, -1, 0, 1, 2, 3, 4, and then I do that for x and for y, that's 6, 4, 4, 4 plus 4 is 8, 8 times 8 is 64. I have 64 dots here. And 64 dots, clearly or maybe not clearly, it doesn't seem like it's enough to describe this. right? So continuing on with this idea of plotting points, if we plot 64 dots, this is what we get. Okay, so usually when we're doing this in pre-calculus, when we're plotting points, we just connect the dots we kind of see. But it's just a simple connecting the dots. Connecting these dots is a little bit more difficult because there's a lot of dots. So let's see if we can add more dots to it. This time I'm taking the halves instead of just whole numbers, -4, -3, -2. I'm going -4, -3.5, -3, -2.5, etc. So let's see how that's going to look like. Okay, again, the view from the top just gives me those dots. So it's 8, 16 times 16. How is 16 times 16? 256. If you're a computer major, you should know these things. This is binary. So 256 dots. Now we get to see the shape a little bit better looking, right? So that's a little bit better than our first stab at it. So let's go even more points. This time I'm adding a couple more points. I'm going by increments of 2.5 or 0.25. So again, looking at it from the top, you just see a bunch of dots. So if I go from -4 to +4 in increments of 1/4, how many dots do I have there? A lot. But now we get to see how it really looks like, right? Is somebody figuring out how many dots I have here? That was the last time. From 256, I added, I guess, another 256 dots, right? 512, maybe? So imagine going from really sparse to a little bit dense now to something that's pretty dense. You can kind of see the picture of how this graph should look like. 4 times this? And 24 dots. By the way, those are all powers of 2. Again, if you're a computer science major, you should know these things. If you look at the number of megabytes, bytes, megabytes, gigabytes, or something like that, on the computer, they're all based on these powers of 2. Like 64, 32, 64, 256, 1024. Those are all powers of 2. Anyways, if you were to connect those dots, you finally get to see the actual surface. And this is our saddle. Whoops. Whoops. So this is your graph. Your dots connected. And then your surface filled in. Or areas, I guess. And then you have your saddle. Okay? So obviously we're not going to be plotting points. I just wanted to show you the whole idea of plotting points, because if you have a computer like this, or if you have a program like Mathematica, you can certainly just plot as many points as you want to get a visual of how this graph is going to look like. But realistically, that is a more difficult approach. And so what we're going to need to do is we're going to need another method of visualizing the graph of these things. So let's think of another method of visualizing the saddle. Assuming that we don't know anything about the saddle, how can we visualize this? And to begin visualizing this, I want to go back to that numerical table that we had. Where we had zeros, I think we had 1, 1, negative 1, negative 1. And then we had 3 somewhere, right? Where do we have 3? Diagonal to the 1. And then we had negative 3 over here. So there's something interesting about these. Remember, the inside of the table are z values, and then you have x and y out here. Okay? So if you take this idea and look at the xy plane as this two-dimensional grid, and then look at z going up and down, imagine that your z value of 0 forms this x in your graph, right? And then a z value of 1 would be up here somewhere. And then a z value of 3 is over here. So a z value of 1 happens here. And then if you take a look at the z value of 3, somewhere between 0 and 3, you're going to have to cross 1, right? You're going to have to cross 1. So there's going to be another z value of 1 kind of hanging out there somewhere. Do you understand what I'm talking about? It's almost like it, yeah. It is. It's tracing. I was trying to be a little bit more dramatic here with the numerical values. So what we're actually doing here, or what we can do, is what did you call it? Tracing? There is a fancier name for this when we're dealing with functions of several variables. When we're dealing with, like, remember when we're in Quartix, where we would cut it using different planes? That's what we would call tracing. So this is essentially tracing, but when we're letting z equal to some constants, and z is the output variable, when we're letting the output variable equal to constants, then we're really looking at what's called level curves. Okay? So that means you have this graph. A level curve is a plane cutting the surface, a plane that's parallel to the xy plane that's going to be cutting the surface. A level curve is the curve that results when you cut a plane that's parallel to the xy plane. You use a cutting plane to cut the surface, and then the resulting intersection is going to be your level curve. A z is equal to something plane, yes. So when I say z equal to a constant, what you're getting here geometrically is that this is a plane parallel to the xy plane. And we did this already when we called it tracing. So let's do it again and see if we can remind ourselves what happened. If we let z is equal to 0, we get 0 is equal to x squared minus y squared, and we get x squared equals y squared, and then we get x equals plus and minus y, or y is equal to plus and minus x. And then remember what the graph of that looked like. It was just an x, right? It's y is equal to x, y is equal to negative x. So those are just two lines. Two lines that cross at the origin, and that's your level curve z is equal to 0. What happened? So that's one level curve. Let's do another level curve. Z is equal to 1. This is what I was trying to explain here numerically. But when z is equal to 1, you get x squared minus y squared. And so if you remember what this is what? Hyperbola. Centered around the origin. Remember, x squared minus y squared, or think about it as x squared over 1 squared minus y squared over 1 squared. And when x is equal to 1, this would make sense. Y is equal to 0, that would make sense. But when x is equal to 0, that would make sense. So x equals 0 doesn't happen for that. So these 2 points, I guess I should have tilted this. I should have tilted my table to make the x go vertical and y go horizontal. Anyways, so that 1 that I was looking at over here are these 1 points, and then remember I was trying to squeeze in a 1 between the 0 and the 3, so it's like squeezing in a 1 over here between the 0 and the 3. Yeah, it's like the intermediate value theorem. To pass from 0 to 1, or to pass from 0 to 3, you have to pass through 1. Okay, we could do another level curve. z is equal to, by the way, it's always good to label these level curves, especially these level curves that break off into a couple of pieces. It might be good to label them at those separate pieces. And then we could do z is equal to 3, because I'm looking at 3's over here, but I don't. You can do 2 or 3 or whatever. Let's do 2. 1 is equal to x squared minus y squared. Oops, not 1, but 2 is equal to x squared minus y squared. So that's just another parabola that's, or hyperbola that's moved over a little bit. Okay. All right. Now let's try negative numbers, because we should be able to put negative numbers in here. Negative 1 is equal to x squared minus y squared. That, to me, that kind of looks like a hyperbola, but we're used to having hyperbolas and ellipses. We're used to having 1 over on the other side, not negative 1. So if you just want to make it look like a hyperbola that you're familiar with, just divide out a negative sign, and then you get y squared minus x squared. So now the orientation of this hyperbola is going to change, and that is going to give us a hyperbola that opens up down instead of sideways. So z is equal to negative 1. And then if you can imagine putting more negative numbers here, you're going to get more hyperbolas. Okay? So that's how we can view level curves in that way. So the z values, when you let z equal to constants, it's good to let them constants as long as they're in the range of this. So we still haven't really talked much about the domain and range of things, but we'll see if we can talk about that in a few minutes. Is this cool? Now, I don't know if you guys have, most of you don't have Mathematica, and a lot of you guys probably don't have the graphing calculator program that I use, but this is available online. As long as you have internet connection, you can always take a look at this, and then you just have to make sure that you're Java enabled and all that stuff. But if you click on this, the first example that they have is an example of a function of several variables. And so the example that they give is a nice example with an exponential function, but I'm going to go ahead and change that into the function that we're working with, so we can actually see a nice visual of this once it works. All right, so our function was x squared minus y squared. And let's take a look at the graph of that. So this is a graph of that, and that's what we expected. And I think we can take away the box. Where's the box? Hide box. All right. Graph. I don't have control over this. Anyways, I can also do what they call a contour plot. We went from -2. Let's just go step sizes of 1 and number of contours. -2, -1, 0, 1, 2. So that's 5 contours. So these are the contour plots that we would see, right? And let me redraw that graph. Oh, wait, the contours. The contours are supposed to be here. Can I draw the contours? Anyways, I can graph it using these planes, and I can graph it using the contours. I thought I can graph it using the contours at the same time. Well, the contour is two-dimensional. Say it again? Yeah. Wait, say it again? Uh-huh. Here? I'm not understanding what you're saying. Is there something about this that controls this? Have you played around with it?
No, I was saying you could graph the equation for the hyperbola.
Oh yeah, yeah, yeah. You can do that too, but I wanted to get a three-dimensional picture and at the same time see the contour on the side here. This one? It shows some other stuff that we're going to study later on. Oh, there it goes. So let's take those planes that I put away for now. I think I just clicked on this. Oh, now it disappeared again. So draw a contour, and then I click on this. Oh, there it goes. So if this is too many lines, you can adjust your contour so you're just focusing on just one line at a time. Oh, we can even show the level plane. See a dot on there. How can I adjust the plane? Well, anyways, you can play around with this and see what you can get out of this by changing some of the parameters and stuff. But this is generally what I wanted to take a look at, is to take a look at how a plane cuts a surface, and the result is something that you can see in two dimensions. So I want to also stress the idea that it is important that you know a lot of these two-dimensional graphs. You know, we spent some time on that in Chapter 10. That's why Chapter 10 was important. When we talked about the conic sections, you should know when something looks like a parabola, even if it's going sideways. You should know when something looks like an ellipse or a hyperbola. And you should know when something looks like a circle. Okay? So that turns out to be something that's important for us to be able to identify. Because we're seeing something, we're examining something in higher dimensions, and then we want to bring it down to 2 dimensions so that we can view it. And if you can't take a look at, no, let me take a picture and finish this. And if you can't take a look at an equation like 2 is equal to x squared minus y squared, and then determine that this is in fact a hyperbola, then it's going to be a little bit of extra work for you to try to figure out that it is a hyperbola and then be able to draw it. So being able to draw this is going to be important for us. Okay, we got a nice picture here of the graph. If you take a look at other programs, sometimes they define what's called a density plot. So these are contours, which means if you look at them, you see the graphs of lines. But a density plot tells you something else, because contours, if you don't label them, it's going to be hard to tell whether something is higher or lower. But if you look at what's called a density plot, it just looks all the same. Maybe yellow was gray. It turns out that darker is lower than the higher values. So this would be called a density plot, where instead of giving you, I don't know if you can see the lines. There are lines there. I could see it on my computer. It's harder to see here. But there are some lines that exist here. So there are lines that exist here. And then what happens here in the darker places, lower z value. So the darker places have a lower z value, and then the lighter places gives you higher z value. Say it again? Yeah, so it's showing, if that's how you want to define density, is like the height of the z value, then the lower density is darker, the higher density is lighter. Higher z value. So this is called a density plot, and there's computer programs that have density plots so that you can immediately tell, not just by the outlines of the contour plots, but by the heights of the z values, you could tell which way things are going. Okay? All right, any questions about graphs? So we really dove into this y is equal to x squared minus y squared and examined it, in great detail. So I think it's good to take a look at, let's take a look at a couple of other functions that might look familiar, and then examine the idea of domains and ranges. Well, actually, why don't we start with this one, since we are talking about z is equal to x squared minus y squared, and take a look at domain and range. So with a domain and range, back in pre-calculus, I always told my students that you'll really, for the domain, you need to worry about the domain if you have a square root or if you have a fraction. And then they introduce all kinds of other functions like ln's and stuff like that, where that would also restrict your domain. So you just have to try to remember what those things were that restricted your domain, and then apply it to something like this in 3 dimensions. So in this case, what possible, now I can't just say x values, right? So I have to say what possible x, y values can I put into this function? All real numbers? What is it? No. Do we want to say all real numbers, though? What? Do we want to say all real numbers? No, it's not that. What's my input? XY. So do I want to say all real numbers? What do I want to say? What? So not just all real numbers, because when you say all real numbers, I'm looking at scalar values, right? I want to be able to put in any pair of real numbers. So any xy point that I can think of would go in here. So your domain is the whole xy plane. Okay, the range, sometimes it's called codomain, so it depends on the book and how they talk about it. The range is all the possible outputs. What are my possible outputs? And for this case, how should we put range? R and G would be all real numbers. Can I get positive numbers out of this? Can I get negative numbers out of this? Yeah, so it looks like it'll be all real numbers. So that's my domain and range business. So now let's take it to, let's do a different function that might not have such a nice domain and range. Let's do another problem. Let's do it here. Z is equal to x squared plus y squared. What's the domain for this one? What is it? We can put any number in there and it'll work, right? What's the range for this one? What? All positive? Can we have 0? Yes, no. What? Yeah, you can have 0. How are you going to get 0? So if x is 0 and y is 0, you get 0, 0. Okay, so it looks like our range is going to be all those numbers, including 0. Now let's do another one. All right, so what's our domain? Different for x and y? Maybe. Or yeah, maybe we can use the x and y as a relationship together to figure out our domain. What's the deal with the square roots? It has to be positive, right? So your domain is going to be any xy value that I can put in here that would guarantee that the thing under the square root is positive. So why don't we say 9 minus x squared minus y squared has to be positive. Can it be 0? Yes. That just means z would be equal to 0, and that's all good. So if you want to solve for x and y together, you're going to maybe get x squared plus y squared is less than 9, less than or equal to 9. Be careful with moving the inequality around. What is this? It looks like a circle. What does this less than or equal to do to the circle? Okay, wait, what? It fills in the circle, or is it going to be outside of the circle? Inside the circle? So one way to express your domain here, this you could probably write this and it'll be fine for your answer for the mathematics mathy about it. You can say your domain is going to be the set of all ordered pairs x, y such that x squared plus y squared is less than or equal to 9. And then you can even think about graphing this. Well, the domain is probably going to look like this. And you guys are saying it's a circle of radius what? Radius 3. And it's going to be everything inside of the circle, and including the circle itself, right? Whereas if this was a strictly less than sign, then we wouldn't count the circle itself. So that's your domain. So that means out of all the ordered pairs that you can have on the xy plane, you can only pick from within the circle. In other words, if I try to pick a number that's outside of the circle, like 3, 3, I'm going to be in trouble. Right? If I put 3, 3 in here, I'm going to have a negative number. That's not going to give me an appropriate z value. Okay, the range. Any ideas what the range is? What? 3 and negative 3? Including? Not including? Okay? No? But it's close. Remember, the range is the z values. The z values, right? So the output values. Yeah? So, including 0 or not including 0? Including 0 to... Why did you say 0? Ryan says 0 for some reason.
Because you could get 9 minus 9 and that's
Square root of 0. Well, and then plus, we're taking a look at a square root of something which is positive, right? So we know that it's bigger than 0. How far do we go? Do we go to 3? Do we go past 3? You go to 3. Oh, including? I just put including. Including 3? Yeah. How would you get 3 for z here? X and y were both 0. And is that the largest you can possibly get? Okay. So it'd be interesting to look at the level curves for this. I'll let you do it. All right, let's do one more real quick. What's the domain? So all not real numbers, right? All ordered pairs. So except what?
So that x squared plus y squared is not equal to 0.
And so when is x squared plus y squared equal to 0? So it's going to be all the real numbers except, and sometimes they use a minus sign or sometimes they use a backslash, except 0, 0. So they call this the punctured plane. It's the whole plane, except there's a hole in the middle. Punctured plane, which comes up a lot, apparently. The range, I think that's more of a, well, you can try to graph it and see if you can figure out what the range is. Okay, so this is our introduction to functions of several variables. We took a look at some numerical approaches, some graphical approaches, and then we examined the domains and ranges. Okay, so tomorrow we'll talk more about exploiting some of those ideas for the functions, and then on Thursday we'll review for your exam. All right. See you guys next time.